afternoon, everyone. Thank you for joining us. We are here for the Innovations in Data Science and Artificial Intelligence parallel session. Welcome to our session. I'm sorry, I need my notes. So just bear with me while I actually stop screen sharing for a moment. So I am Nancy Gaucher. I am a knowledge mobilization specialist with the University of Waterloo, working with the Global Water Futures program. This session is being convened by Jimmy Lin, who is here, and you'll hear from him in a moment. I just want to start by acknowledging that we're participating from traditional territories of First People across the country. Here in Kitchener-Waterloo, I'm on the Haldeman Tract, and that was land that was promised to the Haudenosaunee of the Six Nations of the Grand River. The Haldeman Tract is within the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. And I just think it's very important to recognize this. Indigenous culture and values have been really influential in how I think about water, and I think we owe a responsibility to consider this as we meet and discuss about these important topics. Today's event is hosted by our Global Water Futures modeling team. So we have a lot of really great content for you today. I'm going to begin with some housekeeping. The format for today is quite simple. We have 4 presentations. The first is from Jimmy Lin, who's going to be giving a context-based presentation about big data and artificial intelligence applications in hydrometeorology. Next up, we have Chiranjib Chirardi from University of Saskatchewan. Actually, yes, you've just moved to University of Saskatchewan. He's going to be talking about discrete global grid systems as a building block of next generation big spatial data. And third, you're going to hear from Julianne Mai at the University of Waterloo about the Runoff model intercomparison project over Lake Erie and the Great Lakes. And then finally, we're wrapping up with Martin Gauche from Johannes Kepler University. He's got a presentation on deep learning for rainfall runoff prediction at multiple timescales. So the logistics are quite simple. Each presenter has a certain amount of time, 15-20 minutes. If there's time for questions from the audience, we're going to do our best to get to those. I encourage you to use the Q&A box at the bottom of the screen. And we've also hopefully enabled the upvoting feature. So if you really like a question, make sure you upvote that, and we'll make sure that we get to those first. The webinar is being recorded, and it's going to be made available on our conference site later for viewing. And we've also enabled closed captioning. So if you want that, just hit the toggle button at the bottom of your screen. And finally, our hashtag is hashtag GWF2020 if you'd like to join the social media conversation. And I just wanted to also point out that there's a code of conduct in place for this conference. Essentially, we're just hoping for a very respectful dialogue. So if you want to take a peek at that, you can go look at that on the homepage of the website. So without further ado, I'm going to pass things off to our very first speaker, Jimmy Lin. So I'll let him get set up, share his screen, and let him get going. Okay, thank you very much, Jimmy.
Okay, welcome everybody. So my name is Jimmy Lin. I'm a professor of computer science here at the University of Waterloo, and it's my pleasure to kick off the session. All right, so why are we here? Well, I'm here to provide an overview of applying artificial intelligence and data science to hydrometeorology. And this very short talk, the goal is simple. I have the simplest job. I'm gonna set the stage and introduce our fabulous lineup of speakers, Chiranjib, Julie, and Martin, who you'll hear about shortly. Okay, but let's start at the top, right? So what is artificial intelligence, right? This is one of those things where you ask 10 people, you'll get like 11 different answers, right? It can refer to everything from self-driving cars, chess, Go, backgammon, and even poker playing computers, intelligent conversational agents like Siri, facial recognition, object detection systems, smart factories, robotics, smart infrastructure like smart grids, AI-assisted risk assessment, like getting our loans approved, and then what's becoming hot these days, AI-assisted medicine. For example, AI to help radiologists read radiology reports. Now, every time I get to here, I have to sort of say this. I think it's obvious at this point, right? AI is transforming all branches of science, all sectors of the economy, and even the very fabric of society itself. And I don't think this is an exaggeration. But, although there's incredible benefits to society, there's serious dangers and challenges as well, right? So there's no time to get into this, but this is, I think, something that we should keep in mind proceeding forward. Okay, all right, the next question I want to go over very quickly is, well, what is machine learning? Well, in short, machine learning is the subdiscipline of computer science that makes AI work, okay? At the core, in a nutshell, it's about making data-driven predictions. So at a high level, here's how it works. You're given a pile of data, or training data, we call it, that maps from inputs to outputs, X's to Y's, right? And the task is to induce a model that's able to learn from these input-output pairings, right? This is known as training the model, and it's at its core a optimization problem, okay? Well, once you train the model, you can apply it to what's known as inference or testing, where you give the model a new input, X prime, let's call it, something it's never seen before, and you ask the model to make predictions, Y prime. Okay, next question then. What is deep learning? Well, so if you look at machine learning, there are a broad range of machine learning techniques. In fact, if you use linear regression, you are already doing machine learning. Okay, however, the cool kids these days are doing something different. They're doing something called deep learning, which is basically machine learning with neural networks. And it's although it's what the cool kids do, it's only recently become cool again, because modern deep learning is a repackaging of neural networks that have been around for over half a century. All right. So the TLDR is this, right? When people talk about AI, they're really talking about applications of machine learning. Right? And when they're talking about machine learning, even though machine learning encompasses many different things, it's dominated by deep learning today, right? And so at a very high level, colloquial level, some people equate AI with machine learning with deep learning, although they're all distinct. Okay, so AI and applications of AI for hydrometeorology. Well, I mean, many problems can be formulated as spatial temporal prediction problems, right? So as a result, we can bring to bear machine learning, right? Machine learning to the rescue, and in particular, deep learning to the rescue, which is something that you'll hear about in the session. Okay, but there is one more important ingredient, right? That ingredient is this. All right. So if you go back to this what is machine learning slide, you'll see that machine learning is all about making data-driven predictions. And so, of course, the data are important. And in fact, this is something that Oscar the Grouch, and in fact, computer scientists have known for over half a century, right? This is garbage in, garbage out, right? If your garbage data or have issues, well, then you're going to have issues training the model, and your predictions are going to be garbage also, right? And so this is where data science comes in, right? So data science is concerned with the question of how are the data gathered, how are they curated, organized, cleaned, integrated, processed, and a whole other span of a whole other series of verbs. Right? So this is the realm of data science. And not only does data science have to deal with data, it has to deal with data at scale today in the terabytes and even petabyte scale. Right? So I like to think of AI and data science are sort of the yin and the yang. They really need each other in order to get maximal leverage and synergies. Okay, so that's basically all I have to say. I'll very quickly introduce the rest of the speakers. Chiranjab is going to be talking mostly focused on the data science aspects of it, manipulating big spatiotemporal data. Julie is going to be talking about the GRIP-E project that she's been organizing. And Martin is going to tell you about some cool neural network stuff that he's been working on. Okay. Before I turn the slide over to them, one final thing, what you won't be hearing about today, but it may nevertheless be interesting. So there are also projects in GWF that I am involved in with applications of text processing to hydrometeorology. So for example, one of the things that we're doing is applying natural language processing techniques to analyzing the water science literature. Another application that we're working on is taking, in some cases, century-old records, handwritten records of meteorological observations and digitizing them and turning them into machine-readable format. Another project that Julie, Martin, and some other folks and I have been working on is our Cuisinart system, which is a big data system for slicing and dicing your large data sets. So if you're interested, please reach out to me offline, and I'll be happy to tell you all about them. Okay, that's all I have. I have time for questions, and so I will, if there are any, I will hand the moderation back to Nancy.
Great, thanks, Jimmy. We don't have any questions yet, but okay. Maybe I'll give it just a moment.
I'll leave the slide on Oscar the Grouch while we're waiting for questions to come in.
Absolutely. And our panelists can feel free to jump in and ask questions as well. You can just easily unmute yourself if you have any questions.
Okay, so if there are no questions, I suggest we plow the time back into the session for our other panelists for their talk.
Absolutely. Thanks, Jimmy. Thanks so much. You're a great, engaging speaker, as always. So I'm going to allow for Chiranjib to get his slides set up while I just quickly introduce him. Chiranjib Chowdhury was a postdoctoral fellow at Wilfrid Laurier University, and now he's a research associate at the University of Saskatchewan in the Cold Water Laboratory in beautiful Canmore. So Chiranjib, I will hand it off to you now.
Thank you, Nancy, for introducing me. So I'll be talking about what are the necessary requirements for big spatial data, why they are required right now, and how discrete global grid system can be exploited to create such data model, which can utilize the parallel processing and distributed data structure. So this work our spatial lab we have been doing for last couple of years. I was earlier in spatial lab in Wilfrid Laurier University. I'm currently at Cold Water Laboratory. Okay. So there are currently several trends that are currently coinciding. We are sitting on like a vast amount of data, and a major share of that data is geographically referenced. So has a spatial component in it. There are like more data formats than ever. And there is because of the imminent threat of climate change, there is a greater need to monitor the environmental processes in various temporal and spatial scales. Now, this creates an opportunity to create a new tools which can integrate this wide variety of data and perform wide, like complex spatial analysis, and it has to be scalable. But problem is that there is no current GIS or big data technology that can solve these key problems for spatial data. And the progress in large-scale environmental change monitoring is limited by this bottleneck. So To begin, like what are the data models? So to begin with, like we start from a sensor. Sensors gives us a bunch of zeros and ones, bunch of numbers, which are observations. Now, what data model does, it transforms this observation into something which can be directly be ingestible in the algorithm, and which this algorithm or analysis gives us the information or knowledge necessary to conceptualize the information. Now, what are the data model in GIS? So it's a mathematical construct to represent a geographic object or surface as a data. There are various spatial data model such as rasters, vectors, or like spatial time series. Now, as you can realize, these are the multiple conceptualization of the same process. However, because these are multiple conceptualization, we need different analytical tool to process those. So what are the GIS performance issues with the big data? So currently there is no geodata architecture that can integrate uh, very well with the hardware and software big data architecture. There are various data formats or conceptualization that makes it very difficult to integrate them in coherently. The diverse resolution of different data also creates problem for integrated analytics. The distributed storage and parallel processing capabilities are extremely limited in current traditional geodata models, such as rasters or vectors. Sorry. And the performance of different algorithms are not scalable with the number of computing unit and processing volume of the data. So as the data volume increases, the computational expense rises exponentially. So what are the discrete global grid system? So it's a spatial reference system that uses hierarchical tessellation of cells to partition and address the globe. Now, these DGGS can be characterized by the properties of their cell structure, geoencoding, quantization strategy, and associated mathematical function. On a broad level, these are the addressing strategy, like tessellating the globe into different geometric shapes and create an addressing system for those. So there are many different levels, different cell shapes, such as hexagons, diamond, triangles, quadrilateral. Now, every cell shape has their own set of wonderful characteristics. Now, in our case, we are using the aperture 3 hexagon, which has very good characteristic in terms of spatial data, because they have uh, equal neighborhood. And there is one more thing, these systems can be parameterized in terms of the orientation. So as you can see that these quadrilateral in the bottom figure, I, J, and K, these quadrilateral are important for their addressing schemes. Now we want, if we are looking at any location, we want that location to fall within one quadrilateral so that we have a coherent addressing strategy. So in our case, we are interested in Canada, so we rotated the pole such a way that it falls in one of the quadrilateral. So what was our research objective? To create an operational DGGS-based GIS, which is suitable for environmental modeling and analysis of in the big data platform. Evaluate the DGGS implementation of common GIS algorithms, demonstrate the analytical capabilities of DGGS-based GIS for environmental analysis and modeling, and subsequently create a browser-based UI, which will allow user to interact with the system and run different algorithms. And data is right now stored in a centralized server. It's a distributed server called Netiza. So what are the different properties of our, so we call this our system as Integrated Discrete Environmental Analytics System, in short, IDS. So it is based on Professor Kevin and Shahart's DGG-RID. We are using aperture 3 hexagonal cell. And as I mentioned earlier, that it is rotated to cover the entire Canada in one of the quadrilateral. We are using two addressing strategy. One is one-dimensional DGG-ID, which is space filling curve based. And another one is two-dimensional Q to DI. which is two-dimensional IJ spatial um, addressing system. I'll talk about time grid in the next slide. We implemented this system over the on the IBM Netezza, and it has distributed storage and massively parallel from the ground up. And all the addressing indices are integers, which is very good in a relational database system. So we developed the time indexing in similar philosophy as the DGGRID. So we discretized the bounded time we considered from uh, mm, 1800 to 3000, uh, yeah, 1900 to 2000 something, into different segments of different resolution, temporal resolution. So say from 1000 years, 500 years, and up to 1 second. So given any number or any number, we can see what is there is time resolution, and we can track it back from coarser resolution or even in finer resolution. What is their parents and what would be their child. So this is kind of our what is our data model looks like. So it has a central table which has several components: the spatial, the temporal, and the attribute and topology, and the value. And each of these dimensions are connected to a lookup table for each of these dimensions. And the name of the data set is connected to the metadata table. Now this allows us to like slice, because the the spatial considerations are embedded into these lookup tables. So as long as we are respecting those rules, we don't have to worry about the spatial dimension beyond what is already embedded. And that allows a very fast slicing and dicing of the spatiotemporal data. So we convert from traditional data models, from rasters and vectors, or even spatial polylines. We use the uniform sampling, hexagonal sampling, to convert this data into the DGGS data structure. And different rasters and vector operation are very straightforward to implement. The map algebra is very straightforward to implement, because we have cell-based representation, and that creates a set-based operation for the geometry, any equivalent geometric operation. The performance comparison from for the against the traditional data models, we can see like this data model outperforms the traditional data model for various algorithms such as buffer, intersect. It's an order of magnitude faster on IBM Netezza. So this is kind of like what is our system looks like. So we have a browser-based UI. From there, user can choose the data set and the algorithm they want to apply on the data set. And subsequently, it will compute those algorithm in the backend Netezza system and load the output on the same UI. So currently, these are the major data we have been processing: the land cover, the SSMI, the DEM for entire Canada. We have been also working on like developing a flood modeling tool for Grand and Ottawa River watershed. And for that, we are using high resolution 30-meter data. So these are some of the work that we have been doing. So we have been currently doing the land cover and climate dynamics and change analysis. We recently published one system called Inundated, which is about flood extent modeling. We have published a wildfire simulation using cellular automata based on DGGS system and other things. So this is kind of a typical interface will look like. This is for inundated system. It is implemented on 40-node IBM Netezza, and all the algorithms are written in R using the help of deep layer. And the UI and database connection are done through ArtShiny. I encourage you to like go through this link and like test out this system, and if possible, give us some feedback how it is. So there is a user input where user can choose like which location to simulate on and choose the discharge value for which he or she wants to see the return period or flood extent. So this is the structure. The GIS data is converted into the IDS system and is stored in IBM Netezza database. The user can connect through the Shiny UI, and the Shiny UI can communicate to Shiny server, which connects to this database and analytics system using ODBC connection. So user can request the Shiny UI, and Shiny UI transfer that request to the NGO SQL Analytics. NGO SQL Analytics can communicate with the database and retrieve the data required and simulate the flood and return it back to the user. So what kind of next generation system we can think on top of this system? So suppose say like we can think of a decentralized spatial computing system, and where the different players are involved, such as like data provider, the storage peer, the computational peer, and the client. So the data would be pre-processed and stored in a data system, storage system, which can be local data repository, clouds, or even decentralized system. Now the data security and privacy, which can be of hardware, software, or data model itself sits on top of the storage system. The user client can discover the data through browser UI and even ask for an analytics system, which will communicate to this security system and then storage system to retrieve the data it required and perform some analytics and return it back to user. And the output can again be stored in this storage system. That should be it. Thank you.
Great, thank you so much. That was really great. We have a bit of time if there's any questions. I'm just going to give that a moment. If any of our panelists have questions for Chiranjib, you can feel free to just unmute yourself.
Hi, Chiranjib. This is Julie. I would have a question if nobody else has one. That was really interesting. I really liked what you were talking about. I'm just, I think I missed the point. Is what you're doing mostly for like data visualization, or would it also be like that I could come and tell you, I would like to have like the DEM for this and that watershed, and then I could download this subset of data? Or is it mostly like just for visualization, like just in quotes?
No, this system is meant for analytics. So you can think of a, like say, you want to perform some kind of spatial analytics, say like the average over any system, any time duration or spatial extent, or like say you want to perform some kind of like statistics, spatial statistics on the data, is possible to do that. And that's the purpose. It's not the visualization system. It's purpose is to do the analytics on top of the data.
That's super cool. Can I ask a follow-up question then? So do you think that there is like an upper limit of like how large this data set can be, or is it like whatever you develop is basically scaled with whatever hundreds of terabyte large this data set is?
Well, like right now, it depends on the system on which is implemented. So with IBM Netezza, we can do like, I am doing like around 1 terabyte, one single table processing. So, so data volume is not of the problem. Its problem is that how much computational power we have. So with available computational power, it can scale very well. Okay.
And like, is there another question? Then just interrupt me. But I would have, so what you said, like, is that the data you have are like pre-processed on this hexagonal grid, right? Like it's not on the native projection anymore, right? So if I would like to use these data and in the analytics step to run it through mesh, for example, or through another hydrologic model, they all don't understand this kind of grid, right? or I'm not aware of any hydrologic model that would understand like a hexagonal grid. So would I get back like the data in like a more standard format, or how would that work?
Okay, so right now this data stays in the DGGS system, but if it is required, it can always be dissolved and converted to like traditional rasters or like vector data.
Okay.
So not a problem. Like,
okay, cool. Thanks so much. I'm done.
No, that was really helpful. Thanks so much, Julian. So next up, yes.
Sorry, I just have a follow-up question from Julie.
Oh, sure.
I'm interested about if Chiranjeev can talk a little bit about the data accessibility and the metadata standards that he would have used in the data discovery, because he talked a little bit about the metadata. So are we following a standard, for example, the ISO geospatial standard, or how can a student or an HQP access this data or the system if they're interested in?
So right now we don't really have downloading facilities. So for metadata, we apart from like you can see like this system is really new and we need some other information to quickly access the data apart from like what is standard. So as you can see like here, even though the say an user wants to see, say suppose in the UI, user wants to see in some location what kind of data is available. So to quickly access that data, we need to store its location, like the bounding box of the data, and even other information like the resolution, which even though like the data set itself has this thing embedded, like any ideas data model, as long as you know one member, you know what is the resolution, what is their location, but still having that as metadata will allow us to quickly discover the data. So we are still working on that, like what would be the optimal number of parameters that should be stored in the metadata itself. Does that answer your question?
Okay, thank you. And do you have plans to how this will connect into the broader global water futures system in terms, for example, Global Water Futures is building their catalog, GWF.net, and I'm curious to see how what you're doing will talk to what already exists. And be now that you're based at USAS, you know, this is something that it would be really interesting to see how
well, like as long like when the scientists will be like more concerned about the like from development of the model, scientists will go into the how to utilize the results, then this system will be more relevant. With given results, say like the hydrological, the climate information, this system can compute the analytics, the spatial analytics for like major amount of like very fast and for a very large spatial area. I'm not sure like at which stage GWF is currently running. We are working, like currently I'm working on mesh modeling system, and hopefully like the results I'll be able to convert that and into this system and store it for subsequent analytics. Does that answer your question? Hello.
Thank you. I will connect with you to follow up. But
Sure,
thank you very much for clarifying.
Yeah.
Okay. Any final thoughts, questions? Okay, let's move on. Thank you so much, Chiranjeev. That was really great. Next up, we have Julianne Mai, and you've already heard a little bit from her. She's a research assistant professor at the University of Waterloo and a core modeler with GWF. And you have already heard that she's made great contributions to big data through Cuisinart and also Casper. So with that, I'll let her take it away.
Awesome, perfect. Thanks for the introduction, Nancy. You can see my full screen and the slide, right?
Yes, it looks great.
Okay, perfect. Perfect. Hi, everybody. So I'm going to talk today about the big data aspect when it comes to modeling itself. And in this case, it's a model intercomparison study, or actually 2 model intercomparison studies we are running since a couple of years within the IMPC project of GWF. And it's not just me, but it's like a really large group of external and internal collaborators who are working on this. I listed all of them here. I hope I didn't forget any names, since the group is growing and growing. So these people meet basically once a month, and we are trying to compare our models over a common domain. So that's what I'm going to talk about. First of all, why are we doing model intercomparison studies? There are so many model intercomparison studies out there, and you might ask, like, why do we need another one? So model intercomparison studies usually serve multiple purposes. One of the most popular ones is certainly that you are seeking a model that is most suitable for a certain domain. But also it is known to basically compare different kinds of models, like very complex versus data-driven models and so on. Or simply to bring people together who usually don't work together and exchange knowledge and experience, since just to develop standards of how to set up a model, what is the best way to calibrate models and things like this. And due to that, since so many people are usually coming together in a model intercomparison study, you can also access or work on or address the impact of the skill of the modelers on the model performance. So you would give the same model to 2 different groups who are independently setting up a model, and most certainly the model output or the performance of that model will be completely different. So you can address that as well in model intercomparison studies. Now, what we are doing here, what I already said, is that we are working on 2 different studies. We started a couple of years ago with Lake Erie, about 100,000 square kilometer domain you can see on the left. This study is finished, so I will, in short, I will talk about the main results from that study. And when we finished GRIP E, we learned a lot of things during GRIP E. So we wanted to apply those things we found and what we learned in another study. So we decided to extend the domain to the entire Great Lakes, including the Ottawa River portion, which is now about 1 million square kilometers. And I will talk about the status of this in the second half of my talk. So why did we pick that domain? I don't think that I really need to clarify that, because like there are so many people living in this domain, right? It is known to be like one of the largest freshwater reservoirs globally. And we picked Lake Erie in the beginning because like more than 1/3 of that population in the Great Lakes domain is actually living in the Lake Erie watershed, which is known, or Lake Erie is known to be really prone to toxic algae blooms and significantly affected by urban and agricultural management of that domain, since there are so many people living there. So that's why we started in Lake Erie, and obviously the Great Lakes is a natural extension of this. So just a little bit of housekeeping, what we did in the beginning, how we organized the study. We made one major decision right in the beginning, which is that all the participants had to use the same meteorological forcing data. And that was about it. So what we also wanted is that we set up this entire project as like a living benchmark, so that the setup could basically, you could come with your new model, which was not part of the original model intercomparison, but you could apply the same setup, run your model and just see where you are compared to all these other models. And besides that, something that is really important to me is that it is all the other decisions that are made by the group as a consensus. So we are meeting every month, and usually we have one topic where we discuss one specific thing, and in the end we make a decision or we agree, everybody is agreeing on one solution, which we then roll out for the entire study. So that's why it's moving also pretty slowly, because usually it's not me making the decision, but I like to discuss it with the people. So for Lake Erie, since it was like going for quite a long time, the group of people participating grew dramatically while we were running this project. And I just list them here. What I want you to take from this slide is basically that we split this 17 models in total. We grouped them into 3 packages. So there's the first group of models is the machine learning data-driven models. We separated them because they are usually like they are very different in setup and calibration. They follow different strategies. So we wanted to have them separate. The second group of models is basically the models that are all locally calibrated. So they are calibrated at an individual gauge station. So if you calibrate them at 10 individual gauge stations, you would end up with 10 different optimal model setups. While the third group isn't doing that. They have one global setup for the entire domain, calibrated at all gauges at the same time. So that's why, so it's basically the calibration strategy, which makes the 3 different groups of models. As I already said, like all of the participants had to use the same meteorological forcings, which is a reanalysis data set that was provided by ECC. It's a 15-kilometer data set hourly, covering 5 years of data. What we left open to everybody who's participating to pick their geophysical data sets. We made recommendations, but they didn't have to use it. That was basically only to attract this project to a lot of people. So they could basically probably already use a setup they already had and then just like switch to the forcings we wanted them to use. What was also in common is that they had to report their model outputs, the streamflow, the simulated streamflow, at a common set of streamflow gauge stations. So in total, that was 46 gauge stations for calibration, everybody knew. And then after we finished calibration, we also revealed 7 additional stations for validation, where then the participants had to provide streamflow, simulated streamflow for those 7 stations without even having anything calibrated to those. So these stations were split into 2 different groups as well. So we didn't just pick random 46 stations, but we grouped them to be either a station where everything that is upstream is of low human impact. So no reservoirs, no highly managed whatever. So that is 28 stations in total. And then we had the second objective, which is all the most downstream gauge stations. So the ones that are most close to the lake boundary of Lake Erie itself. So those stations are really interesting if you want to simulate lake levels and lake inflows and things like that. So that's why we have that second objective. And the first one, just because natural flows are usually easier to model. So we have those 2 groups. So you will always see results for objective 1 and objective 2. So let me walk you through the main results of the study. First, we are looking only at calibration results. So here you can see the results of the 2 machine learning models we had. You see 2 bars because the first bar is the result for objective 1 stations, and the darker colored bar is for the objective 2 stations. And the height of the bar is basically the median NSE of all the stations that are in objective 1 and objective 2. So what we can see here is that obviously the LSTM models, machine learning models, are way better than the XGBoost models in calibration. I have to say that as well. So that's the first group of models, data-driven machine learning. The second group of models was the models that are locally calibrated, right? So they take every single gauge streamflow observation and calibrate the model exactly to that one. So we have, I think, 7 models for that. they are all kind of similar in performance. We have one model here, the SWOT model that was set up by the US EPA. They only provided results for objective number 1 and never provided results for objective 2. So they are a little bit of an outlier. But here you can, for example, see the human impact in setting up the model, because it's both a SWOT model. One's is set up by the University of Guelph, or people at the University of Guelph, and it's much, much better than the one at the US EPA. So you can see differences like this in there. If you want to see like the very detailed specific results discussed, you can refer to our paper, which is hopefully going to be online very soon, where we published all this. So, and then we had the third group of models, which is the ones that with the global setup, where we again see there is quite some consistency. They are on average have a lower performance than the locally calibrated models, which is something you would expect because they have a global setup and not individually calibrated to each station. But again, there's one model that is like standing out a little bit, which has a way better calibration performance, which is the MHM model in its global setup. And also just the MHM model, in the first, it was set up by 2 different groups, one's locally and one global calibrated, was also the best one in that second group, like slightly better than the other ones. So that is the performance in the calibration for the calibration stations. And then we did a spatial validation. So we couldn't do a temporal validation because we only had 5 years of forcings available. So we picked 7 additional stations that were not used for calibration. But unfortunately, 2 models, the ones that are hashed here, had actually used some of those validation stations. So we should not look at those results in too much detail. But what we can see is the performance of machine learning models is going down in validation. That's something that is expected. We can see that still MHM seems to be outperforming other models, but Mesh SBS, for example, is pretty similar. Surprisingly, actually, the performance of the globally calibrated model actually increased compared to the calibration, but that has something to do that we learned a lot of how to pick stations. And that's something that is tagged by an agency to be low human impact is not necessarily low human impact. So we learned that during this study. So since we had that learned, we picked different stations for validation actually. So that's the main result. That's the average over all stations in objective 1 and objective 2. But if we look now in detail at the performance of all the models that you can see on the y-axis, at every gauge station on the x-axis for objective 2, that was, I think, 31 stations or something. And the color basically indicates what's the performance of that model at that station for the 3 different groups. We can basically see that performance of the global calibrated models, the most complex ones, they don't perform very well for a certain number of stations, and it's the same across all the models. So it really does not seem to be model specific. It seems to be the gauge station that is really difficult. And when we looked in those gauge stations and the upstream watershed, we actually learned that all these stations are in urban areas. So we learn from this that a lot of the more complex models would really benefit for improved urban representation in their models. And they know that, so that's a current development in those models. So again, for more detail, we describe this for calibration validation objective 1, objective 2, all in our paper. To sum up, I talked about all this is that globally calibrated models are pretty good in spatial validation, something that you expect. Locally calibrated models lose performance in validation. That's also something you expect. MHM had a superior quality in all the groups and all the objectives. We had problems in the globally calibrated models in urban areas. And something I didn't show, but what was a very exciting result is actually if you look at the multi-model ensembles we now created for the 3 different groups, we had significant improvements of the performance in all the 3 groups. So the multi-model ensemble was better than any of the individual models did, which is something known, but it was pretty cool to show that in this study. But we had several issues in GRIP-E. I already mentioned we had like a really short forcing time period. It was only 5 years, so we couldn't do any temporal validation. Then the station selection, like how we tag stations to be low human impact versus most downstream, was difficult because we couldn't really trust what the agency set there as values. So that led to like some difficult results in the analysis. And then also we see that different models perform differently, but we actually don't know if it's actually the model or if it is because a model, for example, MHM, just used a way better data set to set up the model than other models. So we don't know if it's actually the model or the data set. And then a criticism during review and just in general is that we only looked at streamflow. So we decided to move on with having this in mind and move on to the Great Lakes. And it's again a pretty large group of people, some new ones, some old ones, a good mix of people, again, like more complex models, machine learning models, and so on. So we decided the Great Lakes, including the Ottawa River, which is this portion up here, which is usually not included in the Great Lakes watershed, but we thought it might be a nice challenge because this one is one that is known to be very regulated. We use a much longer data set now for spatial, for meteorological forcings, so we can actually save some data for temporal validation this time. This data set wasn't available when we started GRIP-E. So that's exciting. We also save a lot of stations, actually 1/3 of the stations we save for spatial validation. This station data set is not revealed yet to any of the participants. And then we will also do an evaluation, means we will evaluate the models at additional data sets, not streamflow, but other data sets. So trying to address everything that was like a concern with GRIP-E. What is also very exciting is that we don't allow the participants to use anymore their own geophysical data sets, but we agreed at the end of GRIP-E, the entire group agreed on a common data set. 1 DEM, 1 soil data set, and 1 land cover data set, everybody felt okay with being used. So this is the ones they have to use now. Again, we are using the same meteorological forcings, which is again the RDRS data set, but the version 2 of it, it has a better resolution. It's again hourly. It's published. So if you want to read a little bit more details, it's under discussion in HESD right now, and it's also available on Casper. So we retrieved the data for the project, cropped it, and merged everything together for the GRIP-GL project. What we also try to, one variability we try to get rid of in the model setups is that we convince the majority of the partners, actually all models except one, are using the same routing product. So this is also going to be standardized. So we are hoping with all the standardization, forcings, geophysical data, routing, and so on, we hope that when we see differences in model outputs, we can actually address it to the model, the hydrologic component of the model, rather than data. So just a teaser for the preliminary results. We again have, we group the models in different groups. We have only 1 machine learning model, the one that was the winner in GRIP-E. It's again, this is right now calibration results, preliminary results. Some models are not yet completely done, and it's not all the models, it's only the models I got results yet from. So then we have again the locally calibrated models that are basically all blue, like really good performance across all the models. We have performance of about 0.8 or above. And then we have models that do a regional calibration. So it's not global for the entire watershed anymore, but it is for, they calibrate each of the lakes individually and then the Ottawa River. So they have 6 final setups in the end. And they are also performing quite similarly. But there's, as I said, a few models are still missing. Once we finish calibration, we will move on to the validation phase, spatial and temporal validation, and then evaluating the models with the additional data sets, which we are discussing right now, how to do this best. So with that, I'm gonna finish, and I'm looking forward to your questions.
Hello.
Hi.
Hi, Julie. I have one question here. Like, I'm also working on like mesh modeling system. So the kind of problem I'm facing, like the downstream stations are kind of like in counterintuitive than the headwaters. So where the glacial melts are significant and downstream has more signature of the rain. So when calibrating, are you like averaging those or like weighted averaging those or doing a multi-objective calibration?
That's a really good question. So we discussed like, so what you're actually asking is if there is like a common calibration scheme for all the models, and there is not, because it would be really, like from my point of view, it would be super unfair to enforce that you have to calibrate your model in a specific way, because these models are also different, right? If you look at, for example, the locally calibrated models, they would never have that problem because they are looking at each individual gauge station individually, right? But everybody has to share their calibration strategy, and usually the people who know that they will end up in the same group in the end, like the regional calibrating modelers, they usually talk with each other. So there is discussion. How are you doing this? How are you doing that? I'm not like, we are like, as the management team, we are not enforcing that. What everybody knows is how they are gonna be evaluated. So everybody knows that what we are going to look at is the median KGE over all the stations, not looking if there's one that is downstream or upstream. It's the median across all of them. And then we will look at the components of the KGE. That's what we agreed on. That was one monthly phone call where we discussed how are we going to compare them. But that's only what we will evaluate them with in the end. I don't enforce that anybody is calibrating against KGE. If somebody thinks it's better to calibrate p-bias in their model because they know the model would be better or works better if this and that is calibrated, or multi-objective or this and that, they can do this, right? Because the modeler itself, the expertise of the modeler comes in there. And I don't want to interfere that. I want to have the best model possible.
Sure.
Does that make sense?
Yep.
Okay.
Thanks, Julie. There's a question in the chat box from Balika. Can you describe some of your data management process and how you will share the data and setups for the project?
Thanks, Balika. So I think what we did in GRIP-E worked really, really well. Like the data sets we are preparing, since it's so much work for such a large domain and sharing it with everybody, we keep all the data project internal until publication. But all these data sets are known to the project members, right? But they stay within the project for the time being, and then will be revealed basically to everybody once we publish them. And what we did is it depends, like if it's model outputs, we will put them probably on Zenodo. That's what we did with GRIP-E. If it is input data, it is usually a little bit difficult because we have to basically contact all the data originators, right? So we will certainly, we will establish all the metadata for these data sets, but we probably won't get like a DOI or will publish them at all because they don't belong to us. We only pre-process them. But what I'm taking care of is that all the data sets we are using are in a standard format. Like I'm downloading the original data with the help of Hongren Chen. Actually, he's a PhD student in the project. We spend so much time in downloading the data, standardizing them, cutting, cropping it to the domain we are interested, to the time period we're interested, and so on. That's the reason why we want to keep them internally for the project for the time being, because it's so much work.
Great, thanks. And I think we might have time for one more question, Kareem. Malik, I have allowed you to speak, so you can just unmute yourself and join the conversation. Maybe while we're figuring that out, I'll ask a question that came in through the Q&A box. Besides streamflow, which additional data sets are you going to compare against?
For GRIP-E, it was only streamflow, but we discussed that in the group, and we thought of 3 additional, like we have 3 candidates for now. We will look how good the results are or how interesting the results are. For now, we are going to use soil water equivalent, surface soil moisture, and actual evapotranspiration. The models will not be calibrated against them. For now, it's how to evaluate them. And then, because that lays the groundwork, because once we know how to compare models against those data sets, it is intrinsic that you then know how to calibrate against them, because you know the metric, you know how to aggregate, disaggregate, whatever. So we decided to first only evaluate, but it's going to be those 3. Yeah.
And Kareem, do you want to try unmuting yourself and asking your question? Okay, maybe what I'll, I think
now it's unmuted. Hi.
Hello. Good
Hi.
That was a great presentation. Thank you. I'm Kareem from Wilfrid Laurier University. I actually found your modern results very interesting, and I'm pretty more interested in the Lstm, the long short-term memory results, because that's a machine learning model, and it kind of beat all the models. So I wanted to know what are the prospects of such models in kind of hydrological modeling, and if you had some challenges with overfitting, and how you managed to have that model beating all the other models.
Kareem, it's amazing. Thanks for this question, because the expert, the person who has set up the LSTM models, is the next speaker. He's also there, like it's Martin Gao. So he can certainly answer all these questions. So he and Jimmy actually had set up those models for GRIP-E, and Martin continues to contribute to GRIP-GL. So Martin, feel free to answer.
Yeah, right. So I think there's 2 things to bear in mind here. So the first one is that the results, or most of the results Julie just showed, were actually calibration results. So that's, yeah, exactly. So this is evaluated on data that the model has seen before. And a machine learning model is, because it's just trained on the data, there's no like physical restrictions as you have in these other models. It can essentially learn everything by heart and just repeat it. So it's easy to get a high value on this calibration period. What's hard is to get a good value or a good results on the evaluation set that it hasn't seen before. And in the GRIP-E project, that was actually sort of challenging because we had only very little data. For the Great Lakes project, we don't know yet how good it's going to work, because we haven't seen the validation results yet. And it's certainly not going to be like a KGE of 0.97, or I'd be very surprised if that were the case.
That would be so cool.
But I think because we have much more data here, it should maintain a sort of a higher KGE or NSE than it did in Lake Erie. And then also we just have more experience by now. So this is also a point that is a difference between Great Lakes and Lake Erie.
Yeah. I mean, still also for the Lake Erie study, like the validation results were not bad. Like, I mean, they decreased, but it still had like some skill, right?
Yeah, absolutely.
It wasn't like the best, but there was still something there. So yeah, it's something I probably not emphasized enough. People didn't get the validation period data yet. So Martin actually needs to wait until everybody else is done with calibration, and then we will reveal the validation data. So he just doesn't know. So like he needs to train the model, and maybe in a month or so, we will know how the validation actually worked. Just to be fair to everybody.
Great. Well, thank you so much, Julie, again. Martin, I'll let you get set up with your slide while I introduce him, which you probably don't need an introduction at this point, but Martin is a PhD student at the Institute for Machine Learning at Johannes Kepler University in Austria. And he works at that intersection between machine learning and hydrology. So I won't take any more thunder away from you, and I'll allow you to just get started with your presentation. Thanks, Martin.
All right. Thanks, Nancy. Yeah, I'll be talking about some work on rainfall runoff modeling at multiple timescales using deep learning methods, and in particular LSTMs. This work is in collaboration with Frederick Kratzer, Daniel Klotz, Graniering, Jimin Lin, and Sepp Hofreiter. And to get started, I think I don't need to motivate to this audience why rainfall runoff modeling is an important task. It's of course useful in applications, anything from hydropower management to flood prediction. And we've heard a bit about this from Julie already, and you might have seen it in other places, that LSTMs and deep learning models in general have shown to be very successful in this application of rainfall runoff modeling. And now, before I go into the details of this talk about modeling at multiple timescales, I'd like to give a very brief overview of what an LSTM actually is. And I'll keep it very high level. So for the purpose of this talk, you can think of an LSTM as actually something that's conceptually kind of similar to a traditional hydrologic model, at least in some sense. And what I mean by that is that a traditional hydrologic model has some kind of internal states that get updated over time as a function of the previous internal state and some input. And then there's some kind of output function that takes the current internal state, and it generates an output from that. And pretty much the same happens in the LSTM. So the LSTM also has an internal state. Here it's called C and H. And this state gets updated over time as a function of the previous state and the input. And then you again have some kind of output function that takes the current state and generates a prediction from that. So in this sense, it's kind of similar to a traditional model, but of course it's very different in the way that we train the model and the way that we interpret the model, because we don't have any physical interpretation of these states or of the parameters that we tune during training, but instead it's all learned from scratch from the raw data. So that's essentially all you need to know about an LSTM, at least for this talk. And now I'd like to talk about the main point of this talk, which is modeling at multiple timescales. And to motivate this, I have this hydrograph where in the blue line, you can see the hydrograph at a daily resolution. And you can see that the flow is kind of low. There's maybe a bit of a higher flow around December 15, but it doesn't look all that high. But then if we look at the same hydrograph at a higher resolution, here in orange, the hourly hydrograph, suddenly we see that there is an extreme peak at the beginning of December 15 that we would have totally missed if we just looked at the daily hydrograph. But this peak might be really important because it could be something like a flash flood where we need to warn people ahead of time. So it's important that we have predictions, not just at the daily timescale, but also at other timescales, especially at higher resolutions. And unfortunately, so far, most of the modeling with LSTMs has been done at the daily timescale. And so in this talk, I'm going to introduce a couple of ways to model at different timescales and also at multiple timescales simultaneously. Now, you might think, well, how hard can it be, really? We know how to do it for the daily timescale. So why don't we just use the same LSTM and just feed it hourly input data, and then we're going to get hourly predictions and call it a day. But it turns out that this naive solution has a number of drawbacks. And to explain these drawbacks, let me explain first how we actually train these models, or how we do inference with these models. The way we do this is we feed the models a history, or sort of a look back window of meteorological forcings, like temperature, radiation, rainfall. And And for daily modeling, usually we use something like 1 year worth of look back. So we feed the model 365 time steps of all these variables. And then in addition, we give it some static information about the basin, like land cover and elevation. And given all that data, it will output a discharge prediction for the current day. And this works great for daily predictions. But as we move to hourly predictions, this 1 year of look back, which was previously 365 time steps, now becomes thousands and thousands of hours that we need to crunch through just to get 1 hourly prediction. And so we get extremely long time sequences that we need to process. And these long time sequences, first, they make training unstable. So it's hard to successfully train a model. And also, they just make it extremely inefficient. So the training and the inference become like painfully slow. Another disadvantage of this naive approach is that in the end, we have two distinct models where one model gives us daily predictions and the other model gives us hourly predictions. But there's nothing that sort of ties these models together. And because there's nothing that ties them together, the predictions that we get out of them are likely going to be somewhat inconsistent. So if I take 24 hourly predictions, they're probably not going to match the corresponding daily prediction, just because why would they? It's two different models. So to address all these drawbacks, what we're proposing in this recent paper is a deep learning architecture that's also based on LSTM that we call multi-timescale LSTM, or in short, MTS LSTM. And before I go into the architecture of that model, I'd like to give the intuition of what it does. And the intuition goes back to this slide where I said that we have this 1 year of look-back data and we have these extremely long time sequences. But it turns out that this high resolution of these time sequences is really only important for the last couple of time steps. But for very early time steps that are a long time ago, I don't actually need that high resolution. It doesn't really matter whether it rained 5 months ago at 2 a.m. or at 4 a.m. It's just so long ago that we might just have it at the daily time scale, and that would be sufficient information. So what we can do is we can process the early time steps at a lower resolution and only the last remaining time steps at a high resolution. And therefore, in total, we have a much shorter time sequence that we need to process, and we're much more efficient. But we don't lose any information because the recent time steps where it really matters, we still process at the high resolution. And that's the idea of multi-timescale LSTM. So in terms of the architecture, it's of course based on the normal LSTM that we know from daily predictions. So we start by feeding in daily values, the look back of 1 year of daily values, just as we would in the normal LSTM. But then at some point during the processing, say today minus 7 days maybe, we take that internal LSTM state and we use it to initialize a second LSTM that then starts to process the remaining time steps at the high resolution, so at the hourly resolution. And because it's been initialized with the daily LSTM, it knows what happened in the past, and it only needs to process the remaining time steps. And of course, this is not something that's bound to daily and hourly frequencies. We can also do this with other frequencies, or we might even have more than just 2 frequencies, like in addition, predict at 3 hourly timescales. This really depends on the application. And because now everything happens within one model, we can now incentivize the model to generate predictions that are consistent, where every 24 hourly predictions average or sum to the corresponding daily prediction, which is something we couldn't do with the naive solution that I showed in the beginning. Another advantage of this solution is that we're able to use per time scale input variables. So if I have a data product that has a daily resolution, I can ingest that into the lower daily LSTM branch here. And if I have data products at the hourly resolution, I can ingest them into the upper hourly branch. And now the hourly predictions will actually benefit from my daily information without me needing to do any kind of manual interpolation to adjust for the different timescales. All right, so let's look at some results. We've evaluated this model on the CAMELS data set. And what you see here is the cumulative distribution of NSE values over a bit more than 500 basins. And these are our two baselines. So the orange baseline is the US National Water Model. So that's a process-based model, no deep learning involved. And the blue line is the naive hourly LSTM that I showed in the beginning. And so this blue line, the LSTM, has the disadvantage that it's extremely slow and kind of hard to train. And if we add the multi-timescale LSTM results, there's two variants of it. I won't go into detail on that now. But what we can see is that we don't lose any accuracy over the naive approach, but we gain a lot of efficiency and the other advantages that I talked about earlier, like cross timescale consistency, for instance. So those are the hourly predictions. The daily results actually look kind of similar, at least from the pattern. So I'll skip over those for now. And finally, I'd like to show one more use case where multi-timescale LSTM is actually useful beyond the timescales application, and that's for forecasting. So in the CAMEL studies that we've looked at so far, we always looked only at reanalysis data where that's sort of observation-based. And so we sort of know all the data beforehand. But in a forecasting setting, we only have data up until the present. So we have observation-based data for the past. And then for the future, all we have is meteorological forecasts. And this leads to some sort of a problem because we have different input data for the past than we have for the future now. And we might not even have the same number of input variables. So we can't just ingest all of this into one LSTM because the input variables the dimensions just wouldn't match. And this is where the multi-timescale idea comes in again, because we can, again, apply this branching concept where we feed the past input data into one LSTM. And then once we reach the point where our observation-based data end, we hand off the processing to a second LSTM that then goes through all the future input data, all the forecasts that we have. And then it generates the runoff forecast. In this way, we're now able to use all of the available past data and all of the available future data within sort of one combined model. And in our experiments, this also turned out to work really well. All right, so to summarize, in this brief talk, I've introduced the concept of multi-timescale LSTM, which is a deep learning architecture that's able to predict at multiple timescales simultaneously at a very high accuracy. And it has the advantage over the naive per timescale approach that it's much faster. And on top of that, you get things like cross timescale consistency, and you can use different input variables at the different timescales. And then finally, the idea is kind of useful even beyond the timescales application, for instance, for forecasting, where you have this discontinuity between past and future inputs. All right, with that, I'd like to close and thank you. And if you're interested in this kind of work, you're welcome to look at our GitHub page, where we also have a Python library that you can use to reproduce some of the results or train a model yourself if you like.
Cool, thanks, Martin. That's really great, very clear presentation. So we'll open it up for questions for Martin, or if you have questions for any of the other panelists, that works as well. You can either raise your hand, and I'll try to keep an eye on that. Kareem, I think your hand's raised from last time, right? Julianne, did you want to ask a question in the meantime?
Yes, I would like to ask a question. Thanks, Martin, for that really also visually very appealing talk. I really like that. I have a question about like when you said that variables could be like you could handle now variables that are available at different timescales. So let's assume that your precipitation is hourly and temperature is only available daily. How would that work? Like, I mean, aren't you like assuming that at one point you switch from hourly or from daily to hourly? So like, how would that work if temperature, you need temperature, or like probably you want to use temperature, but then you're running everything on an hourly time step, but you don't have hourly temperature. Would you then not use temperature at all anymore, or like as a background signal? I don't know. Is that clear what I mean?
Yeah, I think I know what you mean.
Mhm.
So the idea of this per timescale input is actually not to have, or yeah, is actually not that you would have like rainfall at one resolution and temperature at another resolution.
Mhm.
But I think the most promising thing you can do with that is if you have multiple meteorological products that, like, if you have two rainfall products and one is daily, one is hourly,
Oh,
and then
yeah.
you can use one in the daily timescale and one in the hourly one, because we
Okay.
know from just daily modeling that we can hugely improve our performance if we use multiple forcing products. And
So
this way
multiple precipitation. Yeah. Okay.
Exactly.
Yeah. Got it.
if you have, like, of course, it might actually happen that you just don't have rainfall at the hourly timescale or something.
Mhm.
What you can always do is just ingest the daily value at every hourly time step. That always works. It's
Okay.
just not going to be as informative as if you had an hourly product, of course.
I see. Okay, cool. Thank you.
I'm trying to hit the mute button. We have another question in the chat box from Balika. Can the different LSTM branches predict up to different lead times into the future? So do you know if LSTM are being used operationally in flood forecasting or other hydromet services globally?
Okay, so to the first question, yes, absolutely. So this is also a nice thing about this this sort of branch concept of the LSTM. You can essentially, if you have say you have hourly forecasts that have a lead time, or meteorological forecast that have a lead time of maybe 2 days, and you have your daily meteorological forecasts have a lead time of 5 days, then you can run that particular branch just up to the lead time that your input data is available up to. And so absolutely you can run each different branch at different lead times. As for the second question, if LSTMs are being used operationally in flood forecasting, yes. So I know that a number of agencies are currently in the process of adopting LSTMs. And I also know that there's a number of like private sector companies that basically have the business model of selling LSTMs to like hydropower providers or any kind of customer that needs flood forecasting. So yeah, absolutely.
Great, thanks. Any final questions? Okay, well, thank you so much, Martin. That was really great. I just wanted to close things off from the session. Thank you very much for joining us, everyone. We had a really great conversation. There's much more conversation to be had with this conference. I'm going to bring up a slide that shows some of the next things. So tonight, you might want to make sure that you check out the virtual water art gallery. I think that's going to be really cool. Tomorrow, there's a full program as well. We have a 2-part panel series beginning at 11, and then it starts again at 3:15 with some really great speakers talking about pan-Canadian solutions for water security. Once again, there's a full program of parallel sessions. The networking event, I really encourage you to try that out. I tried it yesterday and it was really cool. So I encourage you to think about that. If you have other questions for our panelists, feel free to email them or message them quickly here now, and make sure you get your contact information. I'm sure they are very willing to continue these conversations. I also want to thank Jimmy Lin for all of his work that he did pulling this panel together, along with Balika. She did a lot of work as well. Thank you to our speakers, Jimmy again, Taranjeeb, Julianne, and Martin. You guys did great. And finally, thank you to everyone for joining us today. We really appreciate it. Thanks for coming, and hope to see you again soon.